This paper explores the effect of chiral monomer ratio on the self-assembly of biodegradable nanoparticles prepared through polymerization-induced self-assembly (PISA). While previous studies have demonstrated the efficient preparation of nanoparticles using N-carboxy anhydride (NCA) PISA, the influence of chiral monomer ratio on the resulting nanoparticles has not been fully investigated. The authors introduce a chirality-controlled PISA (CC-PISA) method to adjust the morphology, secondary structure, and biodegradation rate of PISA nanoparticles by altering the chiral ratio of the core-forming monomers. The CC-PISA method allows for the preparation of more adjustable nanoparticles that are applicable for future biomedical applications. The authors use a PEG45 macro-initiator chain extended with L and D-phenylalanine Phe monomers in different molar ratios to prepare homo- and hetero-chiral Phe peptide block copolymers. Homo-chiral formulations self-assemble into vesicles, while hetero-chiral formulations form larger nanoparticles with various morphologies. Surprisingly, using an equal enantiomer ratio inhibits PISA and leads to a polymer solution instead. The secondary peptide structure, specifically the ratio of A helix to B sheet, and pp stacking interactions affect the polymer self-assembly process. The paper also discusses the importance of PISA in preparing biodegradable nanoparticles, which have various biomedical applications such as drug delivery and disease treatment. PISA combines polymer synthesis and self-assembly in a single step, allowing for the preparation of nanoparticles with different morphologies and chemical compositions. PISA is conducted at a relatively high solids content, making it more efficient compared to other self-assembly methods. The NCA-PISA method, in particular, utilizes the ring-opening polymerization of N-carboxy anhydrides to prepare biodegradable nanoparticles. Finally, the paper investigates the effect of polymer chirality on the enzymatic biodegradation rate of the PISA nanoparticles. The results show that the biodegradability of the nanoparticles can be controlled by adjusting the chiral ratio of the core-forming monomers. This finding has implications for potential future applications in drug delivery, where the drug release rate can be adjusted by controlling the nanoparticle biodegradability. In conclusion, this paper introduces a chirality-controlled PISA method and demonstrates its effectiveness in controlling the morphology, secondary structure, and biodegradation rate of PISA nanoparticles. The findings have important implications for the development of biomedical nanoparticles with adjustable properties. Morphology of nanoparticles formed from homo-chiral and hetero-chiral formulations. The figure shows digital images of the final dispersions and solutions obtained from THF at 15 Wt% with varying L-Phe-NCA content ranging from 0% to 100%. The images demonstrate the effect of monomer chirality on the self-assembly behavior of the PEG45BP, D, L-Phe, X-block copolymers. Homo-chiral formulations with either L-Phe-NCA or D-Phe-NCA self-assembled into vesicles, as indicated by the red borders in the images. On the other hand, hetero-chiral formulations with equal amounts of L-Phe-NCA and D-Phe-NCA did not self-assemble into nanoparticles and resulted in a polymer solution instead. The type of nanoparticles formed from the hetero-chiral formulations varied depending on the L-Phe-NCA content. When L-Phe-NCA content was between 10% and 90%, compound micelles were observed. When L-Phe-NCA content was either 20% or 80%, disrupted compound micelles were formed. Finally, when L-Phe-NCA content was either 30% or 70%, swollen compound micelles were observed. These results demonstrate that the chirality of the core-forming monomers has a significant impact on the morphology of the self-assembled nanoparticles. Reaction kinetics and size distribution of nanoparticles formed from homo-chiral formulations. The figure shows the results of reaction kinetics and dynamic light scattering (DLS) analysis of PEG45BP, D, L-Phe, 10 copolymer formulations with varying L-Phe-NCA content at 15 Wt%. The reaction kinetics were monitored using Fourier transform infrared (FTIR) spectroscopy, showing a linear increase in Mn, molecular weight, with an increasing core-forming block dp, degree of polymerization, indicating good pseudo-living character of the ring-opening polymerization (ROP) process. The DLS analysis revealed that the self-assembly of the copolymer nanoparticles occurred gradually during the reaction, as indicated by the increase in derived count rate, DCR, and stable hydrodynamic diameter, DH, after 120 minutes. The nanoparticles obtained from homochiral formulations had a DH of approximately 500 nanometers, indicating the formation of well-defined vesicles. These results indicate that the chirality of the core-forming monomers affects the reaction kinetics and the size distribution of the self-assembled nanoparticles. Pseudo-phase diagram of nanoparticles formed from homochiral and heterochiral formulations. The figure presents a pseudo-phase diagram of PEG45BP, D, L-Phi, X assemblies obtained via chirality-controlled polymerization-induced self-assembly, CC-PISA, at 15 Wt% in THF. The diagram shows the various morphologies of the self-assembled nanoparticles that can be targeted by adjusting the core-forming block dP and the L-Phi NCA content. The different morphologies include vesicles, compound micelles, disrupted compound micelles, and swollen compound micelles. The diagram demonstrates the impact of monomer chirality on the morphology of the nanoparticles and provides a useful guide for the design of CC-PISA formulations to obtain specific nanoparticle morphologies. Reaction kinetics and self-assembly behavior of nanoparticles formed from heterochiral formulations. The figure shows the results of Fourier transform infrared, FTIR, reaction kinetics analysis and dynamic light scattering, DLS, studies of PEG45BP, D, L-Phi, 10 copolymer formulations with varying L-Phi NCA content at 15 Wt%. The FTIR analysis reveals the progression of the reaction by monitoring the disappearance of the NCA monomer bands. The DLS analysis provides insight into the self-assembly behavior of the copolymer nanoparticles during the reaction. The results show that the self-assembly occurs gradually, as indicated by the increase in derived count rate, DCR, and the stable hydrodynamic diameter, DH, after approximately 120 minutes. However, when equal amounts of L-Phi NCA and D-Phi NCA are used, no self-assembly occurs, resulting in a polymer solution instead. These findings demonstrate the dependence of the self-assembly behavior on the chirality of the core-forming monomers. Secondary peptide structure and aromatic interactions in nanoparticles formed from homochiral and heterochiral formulations. The figure presents the results of Fourier transform infrared, FTIR, spectroscopy analysis of PEG45BP, D, L-Phi, 10 copolymer nanoparticles with varying L-Phi NCA content in THF. The FTIR spectra show characteristic bands in the amide I region, representing the secondary peptide structure of the nanoparticles. The analysis reveals the presence of both alpha helix and beta sheet secondary structures in the nanoparticles, and the relative fractions of these structures vary with the L-Phi NCA content. Additionally, UV-vis spectroscopy analysis provides insights into the aromatic interactions, such as pi-pi stacking, within the nanoparticles. The results show that the presence of an alpha helix secondary structure promotes stronger aromatic interactions, as indicated by a larger redshift in the maximum absorbance wavelength. These findings highlight the influence of monomer chirality on the secondary peptide structure and aromatic interactions in the self-assembled nanoparticles. Enzymatic degradation of nanoparticles formed from homochiral formulations. The figure demonstrates the in vitro enzymatic degradation of PEG45BP, Phi, 10 copolymer nanoparticles using the enzyme trypsin. The degradation process was monitored by derived count rate, DCR, and hydrodynamic diameter, DH, measurements over a period of 192 hours, 8 days. The results show a two-stage degradation process, with an initial rapid drop in DCR and an increase in DH, followed by a slower degradation phase and a decrease in DH. TEM images taken during the degradation process support these findings, showing membrane disruption, vesicle fragmentation, and dissolution of the nanoparticles. These results demonstrate the influence of monomer chirality on the biodegradability of the nanoparticles, with homochiral formulations exhibiting a faster enzymatic degradation rate compared to heterochiral formulations. In this paper, the authors investigate the effect of chiral monomer ratio on the morphology, secondary structure, and biodegradation rate of polymerization-induced self-assembly, PISA, nanoparticles. They demonstrate that by altering the chiral ratio of the core-forming monomers, they can control the nanoparticle morphology, with homochiral formulations forming vesicles and heterochiral formulations forming larger nanoparticles with various morphologies. The authors also show that the secondary peptide structure and pp stacking interactions play a role in the self-assembly process. Furthermore, they find that the enzymatic biodegradation rate of the nanoparticles is greatly affected by the polymer chirality, with increased heterochirality leading to slower degradation. These findings have implications for the design of nanoparticles for biomedical applications and provide insights into the self-assembly mechanism during PISA. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.